So there's a lot of terminology that we use in PLCs that people in computers use, because PLCs are computers, right? You understand that? Now we have two types of computers. One you don't run into much anymore because it takes a lot of electronics to do that. So most of our computers now are digital. Uh, One of the airplanes that I worked on had an analog computer in it. So this is the basic makeup of a digital computer, right? Y'all seen this before? So we have a central processing unit uh, that most people call microprocessors now. When I first got involved in computers, the CPU was actually a big unit. The first computers that I worked on actually had three big circuit boards that made up just the CPU, but that was on a mini computer. If you got into these supercomputers, you'd see that the CPU itself is a lot of stuff. But what they figured out is they could integrate most of that into a single integrated circuit, and this is where microprocessor came into play. So all our PLCs is what we call is technically microprocessors, but in PLCs they call the whole unit that does the processing the what? The CPU. When technically the CPU consists of only one unit of a computer, and that's the guy that actually runs programs. So computers can do one thing in life. You know what that one thing is? A computer can do only one thing. Computers can only do one thing. Anybody know what that is? Run a program. That's all computers do. Run programs. That's all they can do is run programs. Now they can use that program to cause other things to happen, but if they don't have a program, then nothing happens, right? That would just be like the doctor coming in and pulling out your brain, even though everything else is still there. You would be dead, right? You understand that? To a program, slave to a program. So nothing works. This display here on this computer would not work unless there was a program that caused it to work. This drive in here would not work. It would come on, but it wouldn't do anything that was useful unless there was a program that comes in. These programs that are specifically designed to run hardware, we call these drivers. And you see that pop up every once in a while. Down here, when you put a USB stick in, it'll pop up saying installing driver. Sometimes it says driver. And that's because the operating system doesn't support that. So these operating systems are really, really neat. In the old days, we had to literally, anytime we put a new port into the computer, we had all these switches on the side that we had to configure the address and the interrupts and all that other kind of stuff. When they came out with what we refer to as flash memory, you know what that is? Flash memory. It's actually electrically erasable programmable read-only memory. Double EEPROM. When this stuff was invented, this changed the way we did a lot of stuff. It gave us the ability. So up until now, I was looking for I don't have it. Oh no! But the USB thumb drive, that's double EEPROM. Uh, we call it a flash drive because that's the technique of that was the technique they came up with how to reprogram it. They became known as flashing. So one of the things they'll use on your PLC, especially this on Allen Bradley PLCs, that's what they'll see. They'll say you need to flash your ROMs because they'll come out with a new operating system. So they'll upgrade the version of RS Logic 5000, and it's no longer compatible with the ROMs in your PLC. So what you'll have to do is you have to flash them. So this is over here on memory. So basically we have two categories of memory. We have what we call ROM, which is not actually true anymore. And then we have RAM. So anybody know the difference between those two? Yeah, one of them is considered to be read-only, but since Flash RAM came out, since double EEPROMs came out, this is not necessarily true anymore. So even on this computer, every once in a while, it tells me I need to upgrade my firmware. So in the old days, ROMs were ROMs, and if they wanted to upgrade the firmware, they would have to send you another chip with the programs in it. That's the only way you could upgrade the ROMs of your computer. Then they came out with EEPROMs, which has a little window in it. I'll go see if I can find these. It has a little glass window in it, and you can actually look in there and see the wafer. And what we could do with these guys is we could expose them to ultraviolet light, and then we could erase them. And then we could reprogram them, but you had to have a prime programmer. You could not just program them. Then they came out with these double EEPROMs, and these, if the computer's got the right circuitry in there, we can literally upgrade the ROMs in the computer without taking them out. But it's not an easy task. So like on this one, I cannot upgrade them. I have to run an application that's provided by Lenovo that allows me to do what? To flash the ROMs. So now PLCs give you that ability. The Siemens will tell you you just need to upgrade your firmware. So when I hooked up one of the PLCs to this computer, this is running TIA Portal version 15, and the first thing it told me is I needed to upgrade the firmware in my PLC. So I got to be careful on this one because most of y'all are running version 14. So we come in here, and then we have portals into the computer. So a computer would be no good if we could not get information into it, and it would be no good if you couldn't get information out of it. So it's just like the touch screen on your phone stops working. Well, if the touch screen stops working, what good is your phone? No good. Or if the display starts working, what's good is it? It's no good. So we have to have inputs where we can get information into the computer, and then we have to have what? Outputs where we can get things out. So on this computer here, what's my inputs? My mouse, my keyboard, right? What's that? A camera would be an input. So what we do is if we're missing any of these items, then the computer itself becomes what? No good, right? So this is the actual die. This is the actual processor. This is the 4004 was the first microprocessor. So like I said, when I first got involved with computers, we worked on what we call a mini computer, which was basically replaced by personal computers, which is what we have now. But this guy had 3 big circuit cards that we plugged into a bus type structure, which was the CPU. But it was real fast. What they realized is they could start making transistors and stuff and integrate them onto a single piece of silicone, and then they could actually have the circuits that caused this to work, right? You understand? Well, first of all, they started off with basic logic gates. So when they had a machine out at Beach's Machinery that I used to work on, where all the logic was actually, it was just transistors. So to make just a logic gate that inverts, what was done on this thing was very complicated because it had counters and all kinds of stuff. But the logic circuit just to invert, and this is a symbol of a transistor, which is a current valve. Oh, I'm sorry. I'll do it right in a minute. Now this is just an inverter that does inversion. And then this would go, and then we'd come over here, right here. Huh? This is a transistor, but what I'm doing is I'm making a logic gate. So back in microprocessors, we looked at this guy right here. And what was that the symbol for? What? No, this is a symbol for a diode. This is a symbol for a logic circuit called an inverter. So that means if I put a logic 1 in, I would get a what out? A 0 out. If I put a logic 0, I'd get a 1 out. And we talked about those in PLCs, but we didn't talk about them very long, right? Okay. Oops, I need to draw that on over. So this is the makeup of the transistors to just get inversion. And when we first started this, and then this would be connected right here. We have a resistor there so we don't burn up stuff. And this is where the term sinking and sourcing came into play. So if I come over here and I had a resistor right here, guys. Sorry. So if I was to come in here and put a 1 on, what would happen is this 1 would transfer and it would turn this guy here on, and it would let the 5-volt supply come out. And so this became known as the sourcing transistor because it did what? It sourced the power. Now, if we came over here and put a 0 in here, I'm sorry, if we put that was wrong. If we put a 1 in here, it would transfer here and turn this one on right here. And what this would do, it would take the output and just connect it to common. And that was a 0. But current flow was flowing into the gate because so current, the actual voltage had to come from somewhere else, right? You understand that? And this became known as the sinking transistor. If we put a 0, if we could follow this through, it would turn this guy here on, and we're not going to do it. And that would take the 5 volts and put it out here, and then that would and this became known as the sourcing transistor. So that's what we call these sensors now. We call them what? Sinking and sourcing. So a sourcing, right, uses a positive common, and a sinking uses the negative common, which is what these guys right here do. So all these IC. But what happened? And like I said, this machine that I was working on at the Beaches, everything was done with transistors. So we had big old circuit boards, and it would have hundreds of transistors on there because that's how old this was, and all they did was logic. Well, after a while, they figured out they could integrate these things on a single wafer, and then we came out with these little guys right here, which we call a dip because it's got 2 lines of pins. I need a little more space. And then I could come over here. Let's see, this would be, we'd identify this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And this right here would go back to power. This would be +5, and then 7 would go to the common. So what we had 12 pins we could work with. And these transistors are so small, they could literally make all the circuits for an inverter and put it there. So what we ended up with was having 8 inverters. I'm sorry, not 8, 6 inverters inside there, where we used to have all these transistors. Well, integration kept improving and improving. Then they came out with a transistor that we call a MOS, which takes up a little space. So it wasn't long before they figured out how to get the whole everything that's a microprocessor does, or central processing does, they got it onto a single wafer, which means now they can put it in a single pack. And this is where the actual microprocessor name came into play. Now the problem with the microprocessor is still limited for the speed because everything's in there. But what it does, it became a lot smaller, which now gives us the ability to put microprocessors in units that's this big and units that's this big. So this watch right here has a microprocessor in it, right? Small, and it doesn't have the power of this, and this don't have the power of that, right? Because this could have a lot bigger, and it don't near have the power of what we call supercomputers that can do billions of instructions per second. So thank goodness for the microprocessor. But what it is the microprocessor consists of everything that the microprocessor needs. In fact, now not only do we have an arithmetic logic in there, now we have more than one arithmetic logic in there. So now we got a arithmetic logic unit that's dedicated to nothing but graphics, which in my day, when I got involved with this, there's no such thing. So now, and they run multiple cores. We had a server that ran two completely different microprocessors. It was called a dual processor motherboard. I can show it to you over there. We still have our original server. But now they put what we call multiple cores, which is basically everything that's in here, and then they put multiple ones inside the same package. And then they share an internal buses on there, and we call this multiple core processors. Which you really work out. PLCs don't need that. What has really, really changed in computers is this garbage right here. When I first got into computers, everything was done in text. Everything was done in text. You commanded it. You had to learn all these commands to type in commands. The original IBM PC a computer could only have 640K of RAM in it. That was it. That's the maximum you could put in there inside the machine, because nothing was graphics. It was all ASCII code, seven bits per character on the screen. Then we go, what's that? Well, the problem is this stuff right here. These what we call GUIs, these graphical user interfaces, where we come up here and we have these little pixels up here, and we're doing them in 32-bit color, which means every pixel on the screen takes 4 bytes of memory. Every pixel on the screen, and we're doing 1024 by 768, and you start doing that, and you're trying to process all that information. So why our computers are so memory hungry is because of what? Yeah, the operating system that's basically running the internet is an operating system called Linux, which is still what? What's that? It's going to have memory. Now, a lot of video cards have their own RAM on them. But the problem is that when they came out with a new interface for these computers, if it runs out of video RAM, guess what it's going to do? It's going to steal the RAM in your computer. So it's changed a lot. So PLCs don't need all that garbage. PLCs don't need to do videos. PLCs just deal with binary. So what this means is the processor of the PLC is way back there. It don't have to do graphics, right? You understand that? So this is the 4004. This is the first processor that ever came out. It was put in a calculator. So we start off with what we call a wafer, and these things now are 12 inches long. And then inside this, they'll actually etch the circuits inside this, and they do it in layers. It's really, really neat if you ever watch any videos. And then what they do is and it's made out of silicon, and silicon is a lot like glass. So basically all they have to do is just scribe it, and then they just break it, and these individual wafers come out of there. And each one of these would be a microprocessor. So there's actually that's actually a wafer right there. So each one of these little squares is a what? Yeah, but it's a microprocessor. So this is what I just showed you, the dips. And so these are just some older. We don't do it like this anymore. Originally, when they came out with the integrated circuits, they came up with this method right here. And you see why it's called a dual inline package? It's got 2 rows of pins, and they're in line each other. So that's how this got the name what? A dip. Huh? No, they're not called anything. Oh, these are called PGAs, pin grid arrays, but they have different names. I don't know what they call them now. The microprocessors now don't use pins anymore. We'll have to pop one out and let y'all look at it. So what they did is they started off the package itself, and I'll show y'all some of these, was real small. And the smallest we could get was 6 pins, so it'd have 3 pins on each side. And then they went to 8. They went to 8 pins, which would be what? 4 pins on each side. And we can still get those. Those are still very popular in especially for your optical isolators. Then we went to 14 pin, and then they went to 16 pin. Then they went to 18 pin. Then they went to 20 pin using this same spacing right here, this same spacing. So they was getting pretty long. And then they went to a 22 pin. And then after the 22 pin, they jumped to this size right here. And this carried us all the way to 64 pin, which was the 68,000 microprocessor that Motorola put out. It was a 64 pin chip. That thing was about that big. And some people finally got smart and says, well, we're wasting sides, right? You understand? So they decided to turn into squares and then put the pins on all 4 sides. And then they said, well, we're still wasting a lot of space. So then they decided to bring the pins out of the bottom. And so this is what we're doing now. In fact, they don't even use pins now. We'll have to break a motherboard apart. We threw all those computers away. We still got a motherboard. We'll pull one out. Go jerk one of those things out. Well, the pins are actually in the socket now. So desktop computers are designed to be upgraded. These guys right here in your tablets, they're not designed to be upgraded. So desktop computers usually allow you to change out the processor. They'll use it to add RAM. It's really, really easy, more memory in it. They don't allow you to change it. So let's pause this and y'all come up here. Let's get back here. Everybody can get around. So here's the actual microprocessor right here. And this is a heat sink. These things, a heat sink, the problem they try to do is they try to make the components themselves real small, which means they don't have enough surface area to get rid of the heat. And so you calculate thermal resistance almost exactly like you do Ohm's law. So every device, every metals and stuff has different thermal resistance. So the best would be, what do you think the best conductor of heat would be? Copper. Yeah. So if this was a copper heat sink, it wouldn't be this big, right? You understand? Because it has a lot less thermal resistance. But copper, in fact, some of the gamers use copper heat sinks because they're, yeah. Yeah. And they use also liquid cooling on some of them too. Yeah. So, yeah, it's kind of like a gel, man. So this is the heat sink. Yeah, and it's got a thermal paste. Usually it's just a pad, but the problem is these surfaces can't be perfect. So so all the little gaps and everything that might exist, you make a good connection with a thermal transfer paste. Here's the process right here. So the pins are actually in the socket now. No, it just comes out. So I get my finger in there. This is the actual processor. So the processors now just have all these pads on them. They say it's better, but technically it's a lot cheaper to make than try to mount all those pins on there, right? All they do now is just put the pads that the pins are mounted on anyway. And look at the processor, the pins are actually, these are spring-loaded pins, so when you push it down there and lock it down, that makes the connection. You see the little keys right here? And then look right here, see the keys? Yeah, yeah. So I wouldn't know. So it's, well, not Murphy proof. I found out when I was in the service, there's no such thing as Murphy proof. I've seen people trim connectors to make them fit. Honest to goodness. They didn't think about turning it around the other way. So, so yeah. So there's no such thing as Murphy proof. It's just like there's no such thing as water proof. You get something down at the bottom of the Mariana Trench, right? Water's gonna get in. So most of them now don't say waterproof. They say what? Water resistant. Yeah. I'm listening. Well, we do that a lot. This is the actual the microprocessor, and this is the RAM. So here's the RAM. So these are called dual inline packages. So originally the motherboard had all these chips on there, which was the memory. Then they came out with these methods right here. Okay, it's called DDR that we're using now. So DDR, what they realized was that on the clock, used to we'd transfer data on just like the rising edge. Well, they figured out that a method where they could transfer it on the rising edge and also the falling edge. And this became known as DDR for double data rate because it could transfer it, what, twice the speed. And then they came up with a method of staggering the memory. So you notice the little memory slots are different colors. Okay. So what this means is that the way the processor actually reads, it's called dual channel, is that it takes time to access this memory, and the type of memory it is, it's slow. So what we do now is they put like the even addresses here and the odd addresses there. So it'll read from this one, and then the next address will be where? Over here. And what it does, that doubles the speed too. This is called dual channel memory, and you can see the sockets are different. So supposedly, if you only have two of them, if you only have two, you're supposed to put them like this, either in the two blues or the two blacks, and that way you get single channel, right? Yeah. And then when you get another, yeah, and the memory's got to match, by the way. And all they did when they changed it is they moved this little key around. You'll see the key right here. So I think we're in version DDR6, I think now, which is extremely high. So a DDR6 would, if you picked it up, it would look like this. But what you'd notice is what? The little slits in a different spot. Yeah. I did line up the notch, right? And when you push it in, these two clicks. So this is the microprocessor. That's what I do with the processor. Oh, there it is. I'm trying to see the notches. I think there it is right here. Huh? There, back up in it. People say, they think I got eyes in the back of my head, right? Yeah, it'll only sit down there one way, but I can't see the notch. That looks like one right there. That looks like one right there. Don't. You see the way I'm handling this? We don't want to touch this. Yeah. Oh, here we go. Yeah, normally what we would do is we would come in here and I'd wear a static band, but I've been dealing with them a long time. I know how to handle. We are, but we'll probably keep the motherboard just for show and tell. We call this the motherboard. For us, it's the mother of all boards, right? And these are our expansion slots right here. These are basically obsolete right now. This is for the video card right here. So we've gone to a different. We're going to this guy right here, which is a what we call PCI Express. And this is PCI Express also. This is a parallel 16-bit, and this right here only depends on what you can do. So it's the video card right there. Yeah, the video card takes a lot of processing power too. It's got its own processor. It's got its own RAM on there because it uses so much RAM. But the way PCI Express is set up is that if you use all this memory, then it automatically start going into your system memory. So, and I don't know how many cores this has, but all right. So don't know where the ROM's at. We can't hardly see it anymore because it's flash ROM. This is what we call the chips. This is what we call the chipset. This is the guy that's responsible for actually decoding the addresses for everything on there to make sure it runs the motherboard. This guy runs programs, and where the program's got to be at for them to run them. In the memory. This either can be in ROM. So the ROM in your computer is just like your what we call our autonomous operating system, or your autonomous memory. This is the memory you're born with. So every computer, the only thing the processor knows when you turn it on and it resets is to go to a certain address looking for an instruction, and that address will always be in the ROM. And then after that, the whole thing's under control of a program. And eventually it's going to come in and do some things. Normally it runs a little power on self-test, which we can't see anymore. We can see it on our PLC because when you first turn it on, you saw the lights start blinking, and then they start blinking, and so it's doing a little self-test to make sure it's capable of running and there's no faults. One of them, I think, Capri's in them, the red light stayed on, right? And what was happening was it was looking for that module on the right hand side, and we had taken it off. So, but it knew something when it ran its self-test. It knew that something was missing. Yeah, that was in its hardware configuration. So we plugged it back in there as a stopgap, but we could have went ahead and upgraded the I/O on it and made it done. So they're working fine now. Are we okay? This is a Pentium 3, which is obsolete. So this is the basically makeup of a CPU, and we learned this in PLCs. It has a arithmetic logic unit. What's it do? And arithmetic logic unit. So what else does it do? Logic, yeah. So that's all it can do. Move stuff around. It can do arithmetic. It can do math. It can do logic, and then it can manipulate stuff around. Then we have control and timing, which basically just makes sure everything's at the right place at the right time. And then we have registers inside the processor that basically holds data when it's actually being processed. So normally we bring the information in from RAM, this data, not instructions. We bring the information in, put it in a register, and then we add registers together and stuff like that. Are we okay? This is an AMD Athlon. So we're getting more and more complex with these things. They started adding multiple CPUs inside there. We don't call them CPUs though; we call them cores. So I think we're up to 6, not cores, 6, 8. I know we're up to 8. Which, huh? Yeah, on processors, 9-core processors. By the way, that's kind of misleading. About cores, what they do is originally what the processor would do is it would have one program out there, and as soon as we switched it on, it would look for it would go into the ROM memory, right? And it would look for a binary code that we called an operational code or an opcode. And then it would come in and would go into the decoder, instruction decoder, and then it would switch to what we call the fetch phase, and it would go out there. I mean, it would switch to the execute phase and go out there and do what the opcode told it to do. And every program was just single line program, which is what the processor. These PLCs only have one core. They don't need all this stuff, right? You understand what I'm saying? So there's a lot less here that is nice to know. The problem we had though was that the programs, everything that we had to do was in a single program. And then what they decided to do was they say, well, what if we could split this big old program up into individual tasks, and we'd put them over here. And this became known as a thread. So every module that can execute by itself is what we call a thread. So what they would do on these multi-core processors is they would load in the program and they would assign each thread to its own processor. Huh? 16? So, well, but the application, and people don't understand that, the application itself has to be written in threads. If the application itself is not written in threads, then you don't get any advantages out of a multi-core processor. Huh? Server processors, yeah. So we don't need this in PLCs. This is a Pentium 4. We already looked at that, right? So this is the basic makeup. We have a watt in there in our PLC. We have a watt microprocessor. We got 2 types of memory. What's our 2 types of memory? So ROM is going to contain your basic operating system, which is called the BIOS, which is the basic input-output system. This is what gets the processor going, and then sooner or later, it's going to start executing stuff out of what? Now PLCs. So PLCs don't need to load its operating system. So the entire operating system for a PLC would be in what memory, would you think? Well, RAM is rewrite. We don't want to change the operating system. Yeah, so in PLCs, your operating system is actually here. What do we use the RAM for? Huh? Well, we don't write programs into this computer. We write programs outside the computer. Huh? For your software. What's the difference between, so we call this up here, we call this firmware. In the old days, you couldn't change firmware without changing the chip. You literally had to pop it out and pop a new one in. Or we could burn what we call a PROM or EEPROM, but double EEPROMs changed a lot of that. So now we have the ability to upgrade our firmware, but you have to do it with a special application. You can't just do it, right? You understand that? And you always make sure everything's plugged in. So you ever say, no, that's not true. But you can't do it. They tell you to plug it into a power source. You're not supposed to use a battery on your laptops. So what's in RAM? RAM is actually kind of this is actually our read-write memory. So ROM we can't change easily, right? You understand that? ROM we can't change easily. You have to have a special application, and also you got to have the hardware built into the computer that allows you to do that. What's that? Yeah, or at a cash register when they call the super over there to come in and flip the switch. So okay so far. So where are our programs stored at? In this guy right here, that's totally true. So here, if I was to pop that battery out of that thing, I would lose everything I had that wasn't in ROM, right? You understand that? But the ROM is there; it's permanent. That firmware is there; it's permanent. So 90% of the programs right here run on RAM. This PLC right now. Mm-hmm. Oh, really? Yes. Huh. So this guy here is not powered up, right? Now in the old days, the PLC still has batteries in it. I don't know what the battery of this is, but if you lost that battery, then you would lose everything. So in the older PLCs, everything was in RAM. Okay. But these guys right here, that program y'all put in there the other night is still there. I can plug this thing up. I could put the switches on there. I could switch it, and it would still latch. It would do exactly what I had. So I don't have to have a computer plugged up these. These things can set up for, I don't know how long they've been setting up, and the programs are still in there. So the only way we can change the programs in these is to do what? Overwrite them, right? So what does this have to be stored in? A kind of ROM, but you're right. But it's this stuff we call that's designed to do that. So this acts like a USB drive. So what's a USB drive? We call it flash memory, but it's basically just double EEPROM, but it's just designed to be used as memory. But it's a non-volatile memory, right? You understand that? So we got a slot on this thing right here. Can y'all see that? What do you think we can use for that? Yeah, we could put a compact flash in there, not a USB. So the PLCs now, they store it in a non-volatile memory. Yeah. Close to it. But what you got to understand, PLCs don't have to be as fast as our computers, right? You understand? Right. So our programs are technically, when you upload it, when you download it into that thing, it's put into a non-volatile memory. But when you come up here and you actually switch it to run, what do you think it does then? It copies it into the what? RAM, yeah. Because if it didn't copy it into RAM, we couldn't update inputs, we couldn't update outputs, right? You understand that? So this is pretty neat. Like I said, originally they had a battery on the side of it. I guess this does too. Normally the only thing the batteries are used for now is to keep up with the real-time clock. So these things actually have real-time clocks in them. So what does the address bus do? Yeah, and guys, we assign these things addresses, but actually we're out here somewhere. Let me do it. So here we would have a special circuit called an address decoder. And then these are actually the addresses that we see over here. So this one right here might be what? This over here might be input 0.0, right? Because this address bus right now, we're dealing with, I think we're up to 64 bits, I think, on our address bus. Data bus, we're at 64 bits here. I need to go check on that, the size of this bus right here now. So the address bus does what? Selects. Yeah. The control bus, the data bus is what? Yeah, where's the actual communication takes place. So the size of the address bus determines how many things you can do what? Select. The size of the data bus determines how many bits you can communicate in. And the control bus controls the communication. The control bus is very complicated. It's a lot more than this. Let's go ahead and take a break, guys. So I got a 3-bit address bus, which means I can have 2 to the third things on my computer, which gives me 8 available addresses. So right now we're putting out this address right here, which is 4. It's a binary 4. The mailbox that has that same address, it opened up, right? You understand? All the other guys is what? Closed. But the problem is we have to tell the mailbox what we want to do. So here it's generating a signal that says what? Can y'all read that? It says, I'm writing. So all these guys get the same control bus signal, but only one's got its what? It's got its door open. So this guy says, I'm writing. So now the mailbox knows to get information off the data bus and store it. You can't. One at a time. Yeah, only one of them is addressed at any one time. So it's just like your ports. So your ports are riding on this big old address bus, and we got this address decoder up here. And then we might have output 0, output 1, output 2, output 3, output 4, output 5. And I come over here, and if I put a 5 over here, then only that output would be active at any one time, right? That makes sense. So yeah, computers communicate one. We call this. I'm trying to get the name. Half duplex. So half duplex means we got two-way communication on the data bus, but we only have one thing on there at a time. So it's kind of like anybody ever talk on old CB radio or ham radio or something like that? How many people can talk at one time? One. Well, that's the way processors work. Now it's doing it at breakneck speed. So everything's got to be synchronized. So we have this clock, and that's when they give you the speed of the processor, like they say, 2.5 gigahertz. That's the synchronization inside. Outside, we don't communicate near that fast. So that's why we got that dual channel DDR. So we switch back and forth, and hard drives don't move. Mass storage devices are slow. USB, double EEPROM is nice, but the problem is that every time you write to a memory location, it's got to erase it before it writes into it. I don't know if you've ever noticed on a USB drive, if you put it in there, it takes a lot longer to write stuff to it than it does to read stuff off of it. Well, the same thing with solid state hard drives. Solid state hard drives compensate for it by having what we call a cache memory, which is a section of RAM that's actually on the board itself. That is not a double EEPROM. We even do that with hard drives now. We put memory on there, and because when it goes out there and gets data off a mass storage device, it knows it's going to get more than 1 byte, right? You understand that? Y'all know what a byte is? Everybody okay? Have I lost anybody? So what's a byte? It's a group of 8 bits. And memory in computers is arranged in bytes. So every byte has an address. But what we do is the processor has the ability to address more than 1 byte at the same time. It's a really neat feature that it can do it. But one thing at a time, which we call half duplex. Full duplex means we can communicate in 2 directions at the same time. So this right here, what do you think this is? It can. Your slower speeds is half duplex, but this has two sets of wires. It's got one for transmitting and one for receiving. So that's the only way you can do full duplex at the same time if you have what? If you have two complete sets or modulated. So this is a read one. Here I'm outputting address 6. So number 4 did what? It closed up. Why did it close? Because it's not being addressed, right? And then number 6, it's opened up its mailbox. But still, we got to know what to do. And this is where this is just one signal on the control bus. It tells the box I'm doing what. Can y'all see what that says? It says I'm reading. And this tells memory, this box, to take what it's got and put it out on the data bus. So the bigger the address bus, the more things you can do what? You can select. The bigger the data bus, more information you can send during one read or write cycle. The bigger the control bus, the more control you have over that communication. So there's a lot of stuff on the control bus that if you take advanced microprocessors, we'll talk about interrupts and other things that's available to us that makes processing a lot more simpler. We don't use interrupts in this class. So the true ROM holds the basic input-output system, the main operating system. RAM, this is our read-write memory, and of course flash ROM. This has really, really, really changed the way we do things. So now it gives us the ability to save information on these guys right here, right? This used to be impossible. We used floppy disks. I already found some floppy disks. I got some floppy disks over in well, the black ones, those are 5 1/4. The 3 1/2s were different sizes. They were different colors. You can get them. You can get them red. You can get them blue. You can get them any color you want to. Yeah, but they're called floppy disks. But the disc themselves is nothing but a Mylar disc, and then they put it in a jacket that gives it some. Well, that's the way we transported programs. That was the only way we could. It's what it was. It looked like a regular old tape, which I found out we still back up to tape here, by the way. So tape's a reliable media, and that's what he backs up on. He backs up to tape. But anything you wanted to be transferable, you had to put it on what? On that floppy disk, yeah. And then the it did because it was actually touching the surface. It actually wrote on the surface. It worked just like VHS tapes, cassette tapes. If y'all remember those, the disc was exactly the same, except it was split up in tracks, what we call cylinders. So, but these changed things. So now we have the ability to not only transport stuff, but now we can use this as our mass storage devices. So now most of your laptops and these guys have what we call solid state disk drives, and that's all they are, these things. But instead of being serial, this is serial, which means we send information one bit at a time behind each other, right? So these things are extremely slow. Your solid state disk drives are parallel, which means it sends information in groups of bits, and so they're a lot faster, but they're still not fast as regular good old hard drives. Reset, we usually don't see this. The only way we can reset our processor on this is to do what? Turn it off and turn it back on. And then it does what? It usually comes up to a power on self-test. So this has a power up reset on it. Your old computers actually had a reset button on it, which I miss. So every once in a while, these computers still lock up so bad that, and these guys are never off, right? You understand that? And they'll lock up so bad, and you don't have that push button you can press. So you have to, you pull the battery out. The only way you can kill power on these things is to literally do what? Pull the battery out of it. And we don't have that feature on phones. So my wife's Fitbit locked up on her. And they went through those soft boot procedures, and it never worked, so they had to send her another watch. So, booting the computer. This is what we use when we say it's loading its main operating system. We call that booting the computer. Programming languages, machine language. This is the only language the processor understands. So every other language has to be what? Translated. And it's a binary language. So it consists of all these codes. We call it operational codes or opcodes. So when I first got in this, we had a big old chart. I should show y'all that too on the last processor we got that had the actual opcodes on there. And it was just a binary number. If you wanted to add, you would have a binary code you would put in a memory location. And it had to be in the right location too. So basically all the processor does. No, you don't do machine code. We used to dump it out before they came out with this. We used to have a lot more control over these computers than we used to. But when they came out with Windows 7, they took all the neat stuff away. They had a program called Debug, which you could actually get into the RAM of the machine. You could actually change stuff on if you knew how, you could change stuff on your floppy disk. So all those messages that used to pop up on the floppy disk, y'all remember those things? We knew how to change them. So we would come up there and say, your disk is write protected, stupid, and stuff like that. And people say, what? So we figured out how to change those stuff. You can't do it anymore. But so we had a robot that talked in phonemes, and that was just tones that we used to make up words. And you could make that robot say anything. And we had one of our students, he was on advanced students, and we let him turn loose on that thing. He had that robot cussing like everything. It was so. It wasn't. I didn't tell him it was funny, but it was. So it was one of these mobile robots too. So it'd be rolling around, and it'd see somebody and say, "Get out of the way, blankety blank blank." I said, "You can't do that. You can't do that." But it was hard too. So to do this, you had to understand everything in the processor. You had to know its registers. You had to know its capabilities. You had to know the syntax. You had to know all your I/O addresses. You had to know the actual address of everything in the computer. A very complicated language. So this is a machine code language. This is written around the 8086 processor. Well, all the versions of the 8086. Well, can y'all understand that? No, an opcode is a code, but we call them operational codes. So this is a binary code, and when the processor goes into the fetch phase, whatever comes in on memory, it uses it as an operational code. And then it switches into the execute phase, and then it does what it told it to do, and then it switches back in the fetch phase. So in the old days, that's the way the processors run. Fetch, execute, fetch, execute, fetch, execute. The new processors, so you wouldn't go into the fetch phase until the processor decoded the instruction, right? You understand that? And that took a little while. What processors do now is they do what they call prefetch. So while the processor's processing this information, it's loading stuff out of RAM into a thing we call a cache memory. Y'all probably heard of cache before. Yeah. So these guys load all the time. So they're fetch, execute. So they really scream now when they did that. But it's still these codes right here. So they said there's got to be a better way. So they came out with a language called assembly language. And we have a PLC programming language that's almost identical to this. It's called instruction list, IL programming, where we can literally. I made my goal today, by the way. These watches don't, just by moving my arm around. So these guys right here. Assembly language. So this is the same program. This is an assembly language though. Mine's 5,000, but it counts everything you do with your arm. Y'all know that, right? So that's fine. And it counts mine when I roll around. So I don't walk. I roll. I get steps for rolling. Huh? What's that? Pushing with my wheelchair. So this is assembly language. So you still have to know a lot. So AX is one of the registers in the processor. So I'm going to take AX and I'm going to put it in that address right there, which is a hex address. But now it makes it a little easier, right? You understand? Because I'm not dealing with all these operational codes. But I still have to know everything about the processor. This is called assembly language. We have one called we have a program and it's called instruction list that's almost identical to this. So it married with assembly language. Then this is, thank goodness, this is what we use. But this has to be translated. So we would write the program, we'd do all this stuff, and then when we got through, we would run it through a machine code program called an assembler, which would take this high-level language and translate it into machine language for the processor. Then we get into this. These are high-level language, uses terms of expression commonly used in the English language, does not require the knowledge of the microprocessor or addressing. It's translated by either an interpreter or a compiler. So these are all high-level languages. And that's our language. So what language are we writing in? What language are we programming our PLC in? No, we don't. We're not doing with that. Would be awful. I would be back here. Can you imagine writing a PLC program knowing ones and zeros? So what language are we? We're doing a high-level language. What's our language that we're using? What's the most widely used programming language for PLC? Ladder. And they abbreviate it LD or LAD. But we have ladder, we have function block, we have instruction list, we have function diagram. We have several different languages, and I'll show y'all some of those, but still the most popular is ladder. So what do y'all program y'all's PLC? Ladder. Yeah. So that's what we're going to do here. So here's our PLC ladder, our programming languages. So they got a YouTube video. So ladder, LD, sequential function chart, function block diagram, structured text, and structured list. This guy right here is the one that's almost like assembly. Ladder, we use symbols, right? That's the language we use. But we don't, when we download it, what does it do? So this PLC has no idea what a normally open contact is. This PLC has no idea what it converts it, it compiles it over. This PLC, this program application actually says compile. So what a compiler does is it takes the entire program, converts it to binary. You still have your main program. But if I run a simulator like that Logic Pro that I showed y'all, that runs a translator. So it never generates a true machine code program. It's translated on the fly. So a compiler is kind of like the Bible. How many languages is the Bible in? Well, but originally it was written in the Greek. The first version was Greek, right? And then they did what? They translated it over to all these other languages. That's what a compiler does. We still have the original versions out there, right? You understand that? But a compiler translates it over. An interpreter works just like if I was talking to somebody that knew Spanish and I have no idea what Spanish is. Well, I know what it is, but I can't talk it. So I would go through somebody, right? So we'd get an interpreter that would, and that's what an interpreter does. So it translates it one line at a time, and it never generates a true machine code program. So any of these simulators that you run, these PLC simulators, where like that Logic Pro, it runs an interpreter. It doesn't run a compiler. But when you send it to the PLC, it's got to be compiled over, right? Everybody understand that? So let's see what this video looks like. It's coming. This is not in. This is just in these PowerPoints. No, and that's the problem. The problem with a PLC manual, even with the textbooks, is it'll come up and it will use terms that they don't explain. So in a PLC manual, you'll see something called an operand. Y'all know what an operand is? And it'll talk about addressing. It'll talk about compiling. It says, okay, you need to compile that over. Well, what is compiling? All these terms, by the way, are in that dictionary that I have in the front. Oh, dang it. Hold on a second. Where's my PowerPoint? Oh, it's over there. You see what my link says? That's I need to find that one. It's laid out really neat. It's not really complicated. Ladder. Let's see if I have examples in this PowerPoint. So this is the way an interpreter works. So what it does is it reads the line, goes to the interpreter, and then causes a little machine code module to work to cause it to happen. Where a compiler actually takes the program, goes through the compiler, and just includes that module inside the actual machine code program. Oh yeah, there we go. This is an example of structured text. Structured text is very similar to Pascal programming languages. So it's all a text-based language. So this is one method we can program PLC. So we like to program in this language. A programmer, people that came up through computer science, they love this stuff right here, right? They learn all these terms, how to make things true, how to make them false. Actually, this is we can do more with this language than we can with ladder language. This is function block diagram. This is digital, guys. So this right here would be AND logic. I don't see any ORs. So all we do is it says, okay, if this and this is true, then this right here would go what? True. So this is just like digital. So if you took digital and you just have to learn these international symbols, this is the way you could program it. You could actually take a digital circuit that controls the device and you could program it into this PLC. So this would be for people that really know digital, right? This is sequential function chart, and we'll look at these. A sequential function chart basically has steps, and then it puts what's required to move from step to step. There's a lot of people that program with this. A lot of people. Germans love this. So they love this. So you're not dealing with inputs, you're not dealing with outputs or symbols. What you're doing, you're saying, okay, if this input is true, then move to the next step. And we'll show y'all something a little better than that. Sorta, but the robot goes from step to step to step to step. The only time we decide what goes to a step is like if we wait on an input, or we wait on an input, or we update an output. So a robot doesn't say, what do I need to move from that step? A robot usually just goes to the next step, right? So it'll execute this move unless you tell it to. You put it. Yeah, but what we're dealing with here usually is an input, like a sensor. We'd say, okay, if sensor 1 is true, then you're allowed to go to the next step. Yeah. So robots go so that would be like these contacts. So I have to have this contact and this contact and this contact true. Well, you don't even have to write the contacts. All you have to do is just say, if this contact is true and that one, then do what? And by the way, AND is done with this. So you'd say like switch 1 and switch 2, And you would put that, and then if all that was true, then it would go to the next step. You know, so I'll show y'all some of the programs that's written. This would actually be the way it looks, but Siemens made it a lot simpler to understand, and you'll see how easy it would be to program a PLC that way. This is instruction list, very similar to what assembly. And what's nice about this is they're showing you the actual ladder logic that would represent each part of this code right here. I would never program this. And then, of course, then we got the world famous what? Ladder. So I'll show y'all. Let me bring it up real quick. The same symbols. And then this will show us how we would actually wire this up to our PLC. So this is something we're going to have to understand before we actually start wiring, right? Okay. So I know this is a sensor. So on these symbols we use on PLCs, if it's inside a square like that, we know it's a what? It's a sensor, right? It's got one contact. Some of y'all are taking sensors. What's the color code? Not white. This is a 3-wire sensor, so we wouldn't have white on this one. No, we don't have red. We don't have red. Brown is the plus, right? Blue is negative. We don't use common much. Negative, and then black would be the signal wire. So notice here's this wire right here. This goes directly to the 24-volt supply. This wire right here goes directly to the 0-volt supply, and then this right here goes to an input of your PLC, if y'all can see that. So this goes to input 1 on our PLC. So we'll look at that. Anybody know what that's the symbol for? Dotted line means they're all in one unit, so it means they're all together. This right here. Everybody have blueprint ready? What's that a symbol for? That's a symbol for a gate valve, but this is a valve. This is a symbol for a solenoid, so this is a solenoid. This is a directional control valve. So that would be pneumatics. We'll have to learn those symbols too. Okay, guys, y'all take another break. Then we're going to try to play around with. By the way, we need to do a lab form on the lab we did last class.